component of currents in conducting medium, in uniform medium, but practically all the same features in presence of a burden, 2-layer, 3-layer medium, doesn't matter. Now this is the graph of magnetic field itself, which we measure. Let us solve one task. Let us try to understand behavior of both components of magnetic field, both quadrature and phase component, in general, using understanding of distribution of currents. Let us start. Let us start from quadrature component. First of all, let me fix frequency, conductivity. Again, in order to simplify process of thinking, let me rewrite it this way. So gamma fixed, omega fixed. Now, what I can only change? Distance between transmitter and receiver. Small, very small distance. We are here. First of all, what do we measure mainly? So again, I consider both of them. What do we measure when distance is very short, when we very, very close to transmitter? In phase component of the field. Moreover, it's 1. Because I normalized by primary field. Here again, if I wrote it, let me rewrite it more accurately in order to remove misunderstanding. BZ magnetic field divided by primary field. But this primary field. Why it's 1? Very clear. Because primary field is huge, but effect due to induced currents in phase component currents is very small. So that's certainly in phase component prevails. It's in phase component magnetic field, total magnetic field, due to primary source and due to secondary current. Let us look in quadrature component. That's more interesting. And then we will come back. At the beginning, it goes as function of frequency. We know how. How? Proportional frequency. Why? Because currents in a induced currents I naught equal gamma mu omega m 4 pi r squared sinus theta. So here currents proportional gamma mu omega. So let me take it square in order to remove misunderstanding. So gamma mu omega. Therefore, when separation is small, we feel mainly currents near transmitter. And for this reason, this part of the response proportional gamma mu omega. Because measuring quadrature component of the field, we measure field caused by these currents. Are all these currents around are shifted by 90 degrees, proportional gamma, proportional omega. Now I start to increase separation. What would happen in this case? This graph tells us quadrature component starts to increase slowly. Why slowly? Because when separation increases, as in direct methods, depth investigation increases. If we start to feel currents beyond quadrature component of currents beyond of this area. But if you remember from the graph, this current starts to reach maximum, then go down. So that's the reason why when we increase length of the probe, only increase length of the probe, we start to feel influence of more remote currents. And it's seen in this graph. Sometimes we ask ourselves why with increase of separation influence of skin effect becomes, we say skin effect or interaction becomes stronger. Position of receiver does not affect on distribution of currents. Medium does not know anything where you put your receiver. But answer is simple, and this graph suggests it. When you increase separation, depth investigation increases in both measuring in phase component, quadrature component, and you start to feel currents which are already not caused by only primary field, but also secondary fields, which are subjected to interaction between currents. So that's the reason why in some methods, Duncan mentioned M34, we increase separation, we increase depth investigation. That's exactly we do in Schlumberger methods, firing methods. Now, let me pay attention one very important part, low frequency part of spectrum. Simple arithmetics, based on the formula which I am removing now shows the following. Quadrature component of magnetic field in receiver at low frequency part of spectrum, or more precisely when induction number is small, can be presented, let me write down, mu m for uniform medium, 2 pi r cube, cosine theta. It's very simple to check from this equation, gamma mu omega r square over 2 omega minus gamma mu omega r square 3 half omega 3 half, and divide 3 square of 2. And another term. It's approximate expression. We will start to discuss what is written here. Mu m 2 pi r cube, cosine theta, of course, but here primary field minus gamma mu omega r square 3 half, simple coefficient, again omega 3 half, and other terms. This term smaller than previous terms because it's a small parameter. Let us read what is here. Primary field times gamma mu omega. Always it takes place. Why it takes place? This term, leading term, is due to, remember, current I naught. Then there is a correction factor, very small, very small. Let us forget about this term and look here. In phase component, primary field due to current in transmitter, then this correction, then secondary field. Now, very interesting fact. First of all, what is dependence on conductivity? If suppose you at low frequency part of spectrum have coil and able to measure secondary in phase component. It proportional gamma power 3/2. Direct current don't have such sensitivity. We have in direct current method field proportional conductivity or resistivity doesn't matter. First power. So small changes of conductivity results in the same change of the field. Here, power 3/2, not great improvement, but it does improve situation. So if you have changes conductivity 10%, field would change 15%. Now, but there is something else. Something else. What is the dependence of the distance of secondary component in phase component of secondary field? Let us call in phase component of secondary field. Suppose this term is cancelled. Here R cube and here, what is the power? R cube. So this term is independent on the distance. What does it mean? It means the following. If we have two coils separation, a low frequency part of spectrum, and we do measure secondary in phase component, small changes of distance practically does not affect. It's not too bad because the same you will see in time domain. It's natural. But that's not all. If field which you measure slightly depends on the distance, what does it mean from physical point of view? About where are the sources which create this field? Close to the observation point or far away? Now, let us go to gravity. That's a beautiful example, gravity. Tell me please what this table generates gravitational field, correct? At this point I have one value. If I move slightly, what this distance, comparable with first distance, what happens with gravitational field? I move 10 centimeters. Change. You feel it? Now, I'm here. I change 10 centimeters. Will you observe the same change of gravitational field? More or less? Less or more? Why? I'm asking not how field changed. I compare gravitational field at 2 points. Distance between them, then 10 centimeters. You are absolutely right if you are thinking about magnitude. My question is completely different. I don't care what is the value of gravitational field. I only asking ratio between gravitational field at this point and second point. Now I am far, 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 far away. Distance between these points the same. Where your ratio will be closer to unit? Here. Everybody understands? Field will be completely different. We don't worry. So each time when in formals distance disappears, tell yourself, I know where my generators of the field, they are far, far away. You see how physics and formulas go very well, and we slowly approach to time domain, understanding of time domain. So, again, you remember our graph, our maximum of current which moves away, 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 exactly the same, tell us these formulas. Now, so we are discussing the low frequency part of spectrum. Just a second. Now, I am very much eager to consider ratio between useful signal and noise and frequency domain. And that's what I'm going now to do it. But before, let me form some small table. Let us so it's a little about behavior of the field, magnetic dipole, uniform medium, but all these features take place in more complicated medium. You remember, I removed these graphs. When frequency is very high, what happens with induced currents? If I have dipole, I didn't pay attention, but I gave graphs. Dipole, again, distance over skin depth. You remember quadrature component? Remember in phase component? Correct? So when frequency becomes very high, what happens with magnetic field? Sorry? That's quadrature component of the field. It goes through zero. Everything is zero. Why? You remember skin effect when induced currents concentrate near transmitter, it must go opposite direction. So that simple question I didn't discuss. Now table, small table. Low frequency part of spectrum. On the low frequency part of spectrum. Confined conductor, any target, but confined conductor in free space. How quadrature component caused currents in conductor behaves? We discussed it. Gamma and frequency. So, primary field, some function d and omega tau. Not difference of d, geometrical factor. How in phase component magnetic field behaves? Primary field times function d, geometrical factor, deeper body, this function decreases, correct? What is here? I gave you and explain you for confined conductor. It was last century, a few days ago. So let me remind you. You remember ring, we took ring. Quadrature companion has unit plus omega square tau square, in phase omega square tau square unit plus omega square tau square. If low frequency part of spectrum, it will be omega square tau square. Let us remember it. Now, conducting medium. I told you I gave you example uniform medium, but what I'm going to write valid, what I told you is valid for overburden, host rock, combination of them, etc. Again, low frequency part of spectrum, the low frequency part of the spectrum. Now, what we know about, let us call it useful signal R. That's our noise. I pay attention to mining prospecting. Then we'll go for other aspects. Do you remember? It was done very, very recently. Some function B, some constant C times omega, gamma, mu, omega, correct? Gamma, omega, gamma noise. That's tau, our useful signal. What about in phase component? Secondary field. Suppose we do measure secondary field. Few minutes ago I told you it's proportional primary field. Some C1, C2. What is here? Somewhere it's hidden. Gamma and omega power 3/2. In most cases, that's a very correct expression. Now it's time to draw graphs which characterize ratio between useful signal and noise if we measure quadrature and in phase component. And then I will show you how it can be done in any case. I will show you results of solution of forward problem using integral equations, etc., etc., etc. We will throw away and only will discuss results. Suppose, for simplicity, we have half space. We have conductor, symmetrical conductor. We have transmitter loop. And we measure here vertical component of the field. We have two choices. Measure quadrature component or in phase. We have few minutes. So let us do it. Current cosine omega t. Here we have magnetic field Bz equal A cosine omega t plus B sinus omega t. That's in phase component, that's quadrature. Understandable? Because here sinus, here cosine. Equipment measures both. It looks like no difference. Oh no, it will be orders difference from point of relation between useful signal and noise. Naturally, we measure two signals. For example, quadrature Bz equal quadrature Bz noise plus quadrature Bz or body. Gamma noise, tau or body. Let us think what would happen. Let me plot here omega tau, for example. Tau is time constant of conductor. Suppose everything is given time constant or body, time constant conductivity of surrounding medium, distance, age, and size, etc., etc., etc. Let us, as engineers, not mathematicians, we are not able to solve in all cases problem, but it's not too bad to predict what would happen. Frequency, and I will plot here quadrature component BZ due to our body divide due to noise. Do you think it's a reasonable ratio? Does it tell us a lot? Can we expect result, or it's better to stay at home? For sure. So, let us start. Let me start from high frequency. So now more rings, no more rings, almost real environment. The same approach is used for overburden, etc., etc. Now, without calculation, what we can say if frequency is high? Huh? Sorry? Near zero. Everybody understands? High frequency, strong skin effect, all currents were concentrated. You remember our discussion where currents are concentrated? Uniform medium or non-uniform medium. When skin effect takes place, currents concentrated only near transmitter, on the surface near transmitter, correct? So therefore it's zero. Now we start to decrease frequency. Decrease frequency, skin effect, skin depth, skin depth bravely increases, square root of 5. So we start to get some signal. So start to certainly ratio improving. We don't know what is the ratio. It could be less than 1, more than 1, doesn't matter now. Now it doesn't matter. Now, what happens? Now my question. There is a moment when distance from transmitter to our body, let us call still h, divided by skin depth becomes less than unit, skin depth in this surrounding medium. You understand what I'm saying? I decrease frequency, skin depth increases, and there is a historical moment when skin depth becomes greater than depth. True? In this case, also suppose there is a moment when omega tau r becomes less than unit. What happens in this case? What would be behavior of field due to noise and due to our body as function of frequency? Both of them will, again, there is a moment when we are at low frequency part of spectrum, when omega tau less than unit and skin depth is greater than depth. So we are at low frequency part of spectrum for useful signal and for noise. What do we know about behavior of the field? Quadrature component would be proportional frequency. quadrature component due to noise will be proportional frequency. What happens with the ratio? Straight line. No dependence. That's what happens. Just a second. For given ratio of conductivities gamma r over gamma naught. So, as soon as we come at low frequency part of spectrum, you can decrease frequency, but ratio between useful signal and noise remains the same. Now, what about skin depth? Because we also like to speak in terms of skin depth. With decreasing frequency, skin depth increases, it becomes equal 10 miles, 100 miles, and etc., 1,000, but depth of investigation will define by this ratio. For example, even if it's ratio 2, we're already in trouble. Not great trouble, but with trouble, because it means 30% from our noise signal, correct? 2 and 1. If it's ratio 1, we are in deeper trouble. If it's ratio 0.5, even we more trouble. Correct? It means signal due to noise twice more than due to useful signal, and nothing can be done. That's almost dead end. No way you can increase current sensitivity. That if ratio, for example, 0.3, 0.2, 0.4, no way to see confidential conductor, to define time constant, no change. If you increase frequency, you make it worse. If you decrease frequency, as soon as you are at low frequency part of spectrum, you measure with high, more difficulties, but ratio remains the same. Now we will see what happens. And of course, skin depth does not. As soon as skin depth comparable with depth to the target, rest, its influence does not exist more. It could, as I told you, sometimes it could be equal diameter of the Earth, but it will not help. Now let us put ratio between useful signal and noise and frequency domain. So first of all, I hope it's clear that when we are at low frequency part of spectrum, current inside of conductor, current outside of conductor is defined by mainly what? Primary electrical field. That's the physics. Because low frequency part of spectrum, relatively small induction current, primary electrical field plays the dominant role, and inside of conductor, outside of conductor, primary field creates electrical field, but primary electrical field proportional frequency. So ratio between useful signal and noise remains constant. If its ratio large, we can use frequency method based on measuring quadrature component, and we don't need any other methods. If its ratio small, we have to look for other alternatives and other scenarios. That's how time domain method in effect arrived. So, For instance, if I would like, before going to the field, to perform evaluation based on geological information, can I do with equipment which measures quadrature component to expect anomaly, or I cannot, or my overburden or host rock will kill matter? What I have to do? Very simple. I don't need to consider, I sincerely believe it, I don't need to consider complicated boundary value problem. To take known program for conductor, plate, sphere, cylinder, which is close to model in given area, to calculate quadrature component in free space, then that would be with good accuracy, my useful signal. Then take very known programs for horizontal layer medium, for overburden or host rock, or for both. Calculate, that would be my noise. Then take ratio, and if at low frequency part of spectrum you see ratio for given depths would be greater than 1, there is a good chance we will detect. No. Now, when this approach would be wrong, I know place when it will be wrong. At high frequency part of spectrum. Why? Because this approach, what is the approach? Simple independent calculation field due to conductor and due to host rock, and forget about interaction between them. When it's dangerous, at high frequency part of spectrum, but we don't need to measure there. It's not interesting part. It's a worst part, or it's a part where we are in trouble, where we intentionally decrease efficiency of the method. But in this part, it works very well. Now, let us look what would happen if instead of quadrature component, with the same loop, with the same receiver, with the same frequencies, start to measure in phase component. Also, it's very interesting. So again, I compensated primary field completely and measure secondary in phase component. Certainly, total signal in phase component of the field will be equal in phase component noise plus in phase component due to our body. Again, I would like to take ratio. Omega tau. Here, something very funny happens. And the same happens in time domain, exactly the same. Ratio in phase or body. I only, sorry, sometimes I write up, sometimes down. So let us think together. So again, the same conductor, the same surrounding medium, the same transmitter, the same receiver, distance the same, radius of loop or outside, everything the same, only small difference. You use channel of your receiver which measures in phase component. What do you think? What happens at high frequency part of spectrum? Frequency is high, therefore where currents? On the surface, so we don't feel our conductor. So no doubt we will get again lovely zero. No effect from our body. You will measure effect due to host rock, overburden, or both of them. Now, frequencies, you start to decrease frequency, induced currents arise, appears deeper, deeper, deeper. Then it will be a moment when they reach conductor. Therefore, you start to feel conductor. Now, what happens at very low frequency part of spectrum? Huh? Is again zero. Because if induced current in our body decreases very quickly as omega square, but currents which in surrounding medium decrease as omega 3 ½ So let us take ratio omega square over omega 3 ½ For sure we'll got square root of omega. So graph will have completely different form. And it turns out this maximum takes place around omega tau 1. Not exactly 1, but around 1. So there is a window. There is a window where you only see your conductor. Now, I will return back to this question. First of all, let us pay attention low frequency part of spectrum. What happens with skin depth when frequency goes zero? I'm checking many times, but I have to be sure that we are right direction. Skin depth increases, increases, increases. It means depth of penetration of electromagnetic energy does increase. No doubt about it. No doubt. Energy goes down. You will measure, you will see field very great depths. But what is the depth of investigation? Two completely different concepts. Depth of penetration and depth of investigation. Oh, that's something very interesting. So, what is the depth investigation in this place if you are working in such frequencies? Zero. So, zero, simply zero. You don't see anything at all. Except, no, not at all. You see upper part of the layer. You measure overburden or host rock or all together. So, is it on this? Sorry? It's okay. Good. Very good. So, that's one of the, that's very, very good example which is not applied only for in-phase companion. In time domain, it's very depth of penetration of time domain fields and system could be huge, but depth investigation in bad conditions could be extremely small when you don't see your conductor. It's true for direct current method, it's true for frequency, for quadrature in phase, but this example emphasizes how it's important, first of all, to distinguish, not blindly say, oh, if my skin depth is great, therefore depth investigation is great. Be careful, no relation except magnetotelluric, and also sometimes it's very bad. And what is important? Important ratio between useful signal and noise. Now, about this window, about amplitude of this window. Do you remember behavior of in-phase component induced currents? Could you show by finger what is the behavior, what is the, using your finger, behavior of induced in-phase component of induced current in uniform medium. At the beginning 0, then maximum, and then goes 0. Correct? Therefore, distance r, that's in phase component. So you remember, at high frequencies, this maximum where? Here. Low frequencies, it goes down. The same behavior the same behavior of electrical field, because current and electrical field behave the same manner. What is the difference between current and electrical field? Constant conductivity. True? So it's a graph of behavior of in-phase component electrical field which exists at certain place. So that's my Earth surface. That's my in-phase component. Frequency is very high where maximum electrical field is observed. Some shallow, but my body is here. Then I decrease frequency. Maximum is going down. Then there is lovely place when maximum in the area of target. I can get good signal. Then I decrease frequency. My maximum goes deeper. But here we have very small electrical field which creates body. Therefore, I will have in target very small signal. You see how everything is connected. Now, but what is the most important? Most important is, let me take, for example, one case, very specific case. Suppose sphere, radius b, radius RL over b equal 2. So radius, I don't know why 2. I know what is 2. Depth z over b equal to depth 2 times great. It's only example. It's nothing else. Now, then, let me consider ratio conductivities. But for example, this curve, ratio 2, 1000 ratio conductivities, 1000. For such model, measuring quadrature component, you will get, again, 1000 ratio between conductivity of target and surrounding medium. Now, for example, 0.1 nanometer and 100 nanometers. Now, anomaly 2. What does it mean 2? It means there are 30% of noise. But there is a noise. What happens if I measure for the same case in phase component? 40. Is there difference? There is. So you simply don't feel surrounding medium. So and it happens in this range of frequencies. So both, you remember, induced currents in medium are distributed in different manner. Depth investigation has different features, measuring both components. And finally, it turns out, as natural expert, ratio between useful signal and noise completely different. Now, Is it understandable? So if we had equipment which would be able to measure in phase component in spite of presence of primary field, it would be drastical improvement with respect to measuring quadrature component which we measure. It was realized that it's a relatively low frequency. Therefore, in phase component of secondary field is relatively small. Therefore, it's very difficult to measure, at least today. I don't know what happens tomorrow. So, but that was understood. That was the main driving force to go to the third stage of mining method, time domain. Question arose, is it possible to create method which would give the same or better depth investigation as in phase component? Of course, much better than quadrature. That's how we came to time domain. So let me, before now move to time domain. It's of course only review. Everything I described in my books, when I wrote books about methods, magnetotelluric, frequency in transient, induction, mining, of course I did describe. For example, these results were obtained 25, 30 years ago. They were very known because time domain appeared many years ago at the end of the 50s. So, but they show what happens, why we moved from one method to another, for good reasons, fundamental reasons, namely reduction of influence of geological noise and therefore increased depth of investigation. I didn't tell you, but I hope it's clear. If compare these two graphs, clear. Measuring in phase component, you have greater depth investigation. Understandable? It's completely clear because you can take deeper body, but you still will get better relations than measuring quadrature. It must be clear opposite side, either measuring quadrature or in phase, always for given geoelectrical conditions, there is a maximum depth and you are not able to look deeper, and nothing will help. Nothing will help. That's limitation of each method. Can you run with speed 30 miles per hour? No. And method has a limit. So everything is very logical. But goal is only one: improve and improve and improve. So let us approach to time domain. I have transmitter, conducting medium, the electrical constant, mu. I have receiver, R. Let us discuss what happens in this case when current in transmitter changes as step function. Can you help me? Now I consider general case when I don't neglect by the electrical constant. I have conductivity, I have the electrical constant. What do you think? What would happen? Question is, receiver, what I will measure here at the first moment, second moment. What happens in the receiver? Could you describe me in general what behavior of signal in the receiver? Sorry? It's conducting medium, conducting, no targets, nothing. You noticed, it's a good comment. It's a good comment because it helps me to clarify something. When we consider, let us move a little back. When we have considered conductor in free space, time response, function of time, can be presented as some coefficients, dn minus t over tau n. That's typical behavior of currents in confined conductor, and field caused by these currents is described by sum of exponents. Clear? Now also at late stage, what we have? Exponential, one exponent, correct? At late stage, B equal d1 t over tau. That's typical behavior of currents induced in confined conductor, no exception. Now, if we have uniform medium, did we see exponent? No. At late stage, instead of exponential behavior, we have this behavior, for example. So I consider now uniform medium. And let us discuss what we will observe. Since I don't neglect by displacement current, as soon as I turn off current or turn on, doesn't matter, electromagnetic wave propagates, starts to propagate. Now it's not free space, it's the conducting medium. So wave is moving, arrives at observation point. When it arrives, regardless what is the conductivity, it arrives at the moment which is equal distance divided by velocity. And velocity is equal velocity of light divided relative dielectrical constant. For instance, this method is used in dielectrical logging in order to measure dielectrical constant. So, for instance, if the electrical constant of water, it will be 10 times slower. We discussed a couple of days ago about propagation phenomenon. So first of all, during this first stage between time arrival, between between 0 and time arrival, no signal, 0. Receiver keeps silence. In our methods, we discuss it. It happens extremely quickly. We don't see it. Usually we don't see it. Now, second, almost seismic. No signal, then first arrival comes. So no signal, then very, very small first arrival. Very small, unfortunately extremely small. So the first arrival. Third stage, time interval, which is approximately around 6, 8 time arrivals. So if it's a close to transmitter, it happens very quickly. If it's longer, if it's a far away, a little longer. So time arrival equals distance over velocity. So take order higher. This is the range of time when field changes, electrical field changes quickly. It only arrived, changes very, very quickly. Therefore, displacement currents play important role because electrical field with time is displacement current. So within this range of time, we have influence gamma and epsilon. That's radar range where radar systems are working, regardless of the frequency or time domain. Then last range, our range, our. Here, electrical field starts to decrease slowly, and therefore influence of displacement currents becomes smaller, and we do have quasi-stationary approximation. Where field depends on gamma. From physical point of view, from our point of view, which I try to deliver, is we have the following situation. We assume that the electrical constant equals 0, velocity infinite, and we assume at all points of our measurements signal comes at the same time. That's the idea. And from this moment we will start to speak about this part only. First of all, we will consider transient response. We consider transient responses due to confined currents in confined conductors, now in surrounding medium. And then I will consider influence of radius of the loop on the ratio between useful signal and noise, because I didn't tell anything about it, since I'm going, of course, they very much affect ratio between useful signal and noise, measuring quadrature component in phase, but it's not subject. But for time domain, I will discuss it. First of all, we have current transmitter, dipole, or loop, doesn't matter. Let us say dipole. What would happen if we turn off current? Medium have conductivity gamma, mu naught. No more quadrature, no more in phase. We measure only one field. The early stage. I consider uniform medium, then more complicated models. At early stage, as you shut off currents were. Here, the skin effect, we already know the skin effect. Then, So here there is a surface between medium and your contour. So that's where currents. No more transmitter, and current starts to diffuse. And it turns out behavior of diffusion currents is extremely, extremely simple. Let me take graphs. It will be easy. Let us do the following. No more time constant. Instead of it, we will do the following. I will introduce parameter tau over r, where tau, let's back to right here. Tau equals square root 2 pi rho t 10 7. How this parameter was born? How it was born? Let us look together. Can I write square root and here 4 pi gamma time 10 minus 7. Instead of 10/7, I wrote here 10 minus 7. No difference. Only one thing I did incorrectly. First of all, time, it must be numerator. And here, since I invented 4 pi, let me put here up. So, 8 pi square. Now I hope you recognize something. Here we can take out 2 pi. 2 pi out. What is left? Here time. Here. What? What I have to write here? 2. Is it okay if I write 2? Because 8 pi square, 2 pi I took, 4 pi square, 2 pi out, 2 is left. So something mixture. No. Okay. Now gamma mu. Gamma mu. Sorry? Now let us look in skin depth. What is the skin depth? 2 gamma mu omega. So instead of omega time, it's natural because we are dealing with time. Now, time is small, tau is small. Frequency is very high, skin depth small. Correct? So, this parameter tau, which we write sometimes in these people who are accustomed to deal, in effect, it's a skin depth in time domain, and nothing else. Skin depth and time domain. You see the same depends. Now, so let us consider, first of all, we have a few minutes, let us consider behavior of the currents, electrical field and currents. Behavior of electrical field has this behavior. That's electrical field in conducting medium. Do you recognize this behavior? It was before for in-phase companion. No exponential behavior. That's early stage, extremely small electrical field. Then at each point it increases, reaches maximum, and then goes down. What is interesting from this graph? What happens if I start to increase time? Here signal will decrease, maximum will be shifted as usually, as should be, not usually, should be, on the right. So, unlike quadrature companion and like in phase companion, with increasing time, near transmitter you will not have currents. That's very important moment. So where currents appear? At greater distances. Before we stop, let me give you one unrealistical example. You have borehole, cased. Metal, high magnetic permeability, extremely high conductivity of casing. Conductivity, let us say 10.7 casing. Conductivity of rocks, formation 10-1. 8 orders, not 8 times, 8 orders. And let us only mentally imagine experiment. Transmitter inside. You turn off current. Turn off current in transmitter. Where currents first moment appear? Near transmitter. Then currents arise in casing. It's extremely good conductor. Friction is very, very small. So currents will live for a long time, seconds. I know, seconds. In this casing. Practically we will not have currents in formation. But time goes on. Diffusion is observed. And what happens finally, what is not measurable, but that's formulas can show and physics. Currents mainly arise here. And it will be moment, that's the most important. That's the most important. It will be the moment when currents here will be exactly the same as if you didn't have casing. That's the essence of diffusion. It's not surprised they will appear here, but it's very surprising and interesting fact is there is a moment when density of these currents will practically coincide with currents in absence of this casing. What does it mean? Please let us put here receiver. Put here receiver. What this receiver, if I am right, what would happen in the receiver? It will measure magnetic field caused by currents in formation, even 8 orders of conductivity, unbelievable ratio. And what would happen? You will measure magnetic field, which will depend on the conductivity of formation. In other words, casing becomes transparent. Again, it's not realistical case. It takes too long, signal at that time extremely small, but what is important, vitally important, is this idea, this concept is the basis of transient soundings. And that's it. In effect, many years ago, first paper was written about induction logging, in the transient induction logging, in the hope to get through casing. It didn't work, but this idea became, next time, transient soundings on the surface arrived. What also is interesting, 1 minute more, when time is such that induced currents here appear, they don't depend on casing, is it matter where you will measure near transmitter or far away? Transmitter is working or not? You turn off current, it does not work. You have somewhere here currents, you can measure here, doesn't matter. You will get information about resistivity of formation. So this is the method which is a principle independent on separation between transmitter and receiver.